Okay, good afternoon, everybody. It is a pleasure to welcome you to this week's colloquium of the C3.ai Digital Transformation Institute. Some of you may have heard this, but the mission of this institute is to attract the world's leading scientists to join in a coordinated and innovative effort to advance the digital transformation of business, government, and society. It's a partnership of the following lead universities: Carnegie Mellon, KTH Stockholm, MIT, Princeton, Stanford, Berkeley, University of Chicago, and the University of Illinois. With the University of Illinois, Urbana-Champaign, we are pleased to be the leads, and also with our national lab partners, Berkeley National Labs, Lawrence Berkeley Labs, and the National Center for Superconducting Applications, NCSA, at Illinois. The corporate sponsors are primarily C3.ai and Microsoft, but we're also supported by AstraZeneca, Baker Hughes, and Shell. We'll have, for this semester, just one more talk. Next week, of course, is Thanksgiving. And the week after, the last week of the semester, we'll have a great speaker, Kai Guan from the University of Illinois, talking about how important it is to quantify carbon credits so as to give farmers a sense of how to meet targets, and using that for data fusion. And it's a very interesting project with all the national labs involved and so on. Past presentations are repositoried at the C3.ai Digital Transformation Institute. Most recently, we had a workshop on AI for buildings, and both for energy consumption in buildings, but also how do you get clean air inside buildings. And of course, past colloquium talks are also repositoried here. This presentation is a 40-minute presentation for a 15-minute Q&A. Use the Q&A feature to ask questions, and you can upvote a question that you like, and we'll try to answer as many questions as time will allow. I'll be in the room in person, so I think that it'll be Larry who will be running the Q&A session, so that he'll be, because I won't have a laptop in front of me. It is really a great pleasure to welcome one of our newest colleagues at Berkeley, Maria Laura Della Monache. I'll tell you a little bit about her, talking about really, and her title is called Towards the Next Era of Traffic Control, from Theory to Applications. I can think of no other area which has really influenced how we think about digital transformation of societal systems than traffic, broadly speaking, transportation, and logistics. So we're very, very pleased to have Maria Laura here. She has just joined the Faculty of Civil and Environmental Engineering and the Institute of Transportation Studies here. Just prior to this, she was a research scientist at INRIA, the Center for Research in Computing and Automation in Grenoble, and a postdoctoral fellow at Rutgers. She received her laurea from the University of L'Aquila in Italy, and a joint master's degree from L'Aquila and the University of Hamburg, as well as her PhD from the University of Nice, Sophia Antipodes. So her work is both combines deep mathematics, but also on the societal transportation, and the societal transformation of transportation. So without further ado, let me turn it over, and I'm sure you folks are in for a treat. So Maria Laura, it's over to you.
Thank you. Thank you, Shankar, for the introduction. Okay, let me see. Okay, so as Shankar kindly introduced, so today I will talk about a bit the work I've been doing in the last few years in the framework of particularly traffic modeling and traffic control. So as you've seen from the presentation, I just joined the UC Berkeley. So the talk of today will be mostly related to application to and use data and application from the city where I was prior to joining Berkeley, which is Grenoble, France. But at the very end, we'll see briefly, if we have time, a brief application also to the Bay Area. So my talk today will be basically divided in two parts. So the first part will go a bit into large-scale traffic modeling and control. And then the second part will develop a new model still in 2D, but that has different characteristics, and that will help us also move towards online parameter estimation and use that online parameter estimation for traffic modeling and control. Okay, so as I said, the running example into the talk of today will come from the city of Grenoble. So the city of Grenoble is located in the French Alps, and it has we started looking at this problem because Grenoble is known to be one of the most polluted cities in France, even though it's not even among the 10th city in size in France. And this is due to the particular environmental aspect. So the city here has basically, it's in a valley in the French Alps, and is surrounded basically from three mountain range. And so the fact that it's in a valley makes the air circulation really difficult. And so that makes the city very polluted. And transportation is considered to be one of the most, if not the most cause for greenhouse gases emission in the city. So when we look at traffic, so we were interested in seeing what was basically, what are the most polluted, so hence the most congested areas in the city, and in particular in the city center. So here, the city has a very particular transportation system. So you have three main highways that are basically the border of the city. And so everyone that comes into the city or exits the city needs to pass to these 3 points. So one is up here, and the other two are one west and one east of the city. And so much else apart from boundary control won't work in the city of Grenoble in terms of control for traffic. So starting from the city of Grenoble, we wanted to see if we can leverage the particularity of this network to improve a bit traffic, first of all, to forecast traffic and then to control it. So here you see an extrapolation of the city graph. So you have each link will represent a road, and then each node will represent an intersection. And the city of Grenoble has circa, let's say, 50,000 nodes and 98 links. So that gives you an idea on how big is the graph we are trying to analyze. So what I would like to show you today is, so first of all, we started looking at this from an environmental point of view. So we wanted something to try to understand a bit how the pollution was working in the city related to transportation. So we wanted to have a model that looked a bit as air pollution models. So we're trying to find a model as the one you see at the bottom here, in which we want to just to understand the pocket of congestion. We're not interested in particular links or particular road congestion. We just want to try to understand what is the macroscopic behavior of the traffic in that area. And we'll focus for today's talk in the city center of Grenoble, which here you can see that's really the downtown area. And that's where we will use as a running example throughout the talk. So we will see three parts. So the first one is how to design a scalable model. And again, the idea is that we want to use possibly only the network information that we have to have this model, and maybe some boundary data flow. So that is how many people arrive in the city and leave the city, and then try to find the dynamics inside that boundary. Then we want to use possibly this model to do traffic control. So in particular, so how we can address traffic control using only boundary data. And then lastly, once we are able, hopefully, to forecast and control traffic, trying to understand what happens when when we're not in nominal conditions. So what happens when there is an accident, for example, or a particular weather condition or particular event that changes what are the nominal conditions. Okay, so so when you look at traffic, basically a traffic network study in urban setting, there are mainly two types of approaches. There are others, but those are the two are the most common in the literature. So the first one is you have a network representation of traffic, which means that you extrapolate the link, like the graph that I showed you at the beginning of the city, and then in each one of the link and the node, you're going to have one equation. That equation can be a PDE for what concerns me, because I mostly work in a partial differential equation and continuous model, but it can be a discretization of it as well. And then you're going to have coupling condition at each node that will link basically the flow for each link to the flows of each road. And as you can imagine, as soon as you go to a city, even middle-sized like Grenoble, meaning that you're going to have 100,000 PDEs to solve plus 50,000 optimization problem at each node. So the problem gets complicated quite easily. And so it's computationally expensive, it's not easily scalable. And when we are dealing with nonlinear partial differential equation for traffic, the control theory is really not straightforward. If we can even talk already as a control theory, since there are still some theory that's not there yet. So the other approach instead is a bit looks at the, goes to the other extreme. So you take the overall city, you divide it in area of homogeneous traffic condition, more or less. And then there you use what are called accumulation models, in which you just change the number of vehicles based on inflows and outflows. Okay. What we would like to do is, starting from the network representation of traffic, use a macroscopic approach to aggregated, but in this case, not by homogeneous traffic condition. We are interested in the overall city, using the overall city as one area and possibly finding by ourselves the dynamics of traffic inside that area, without predetermining which areas is congested, which area is not congested. So, and that's what we will try to see in the first part of this talk. So how, if that is possible and how we can do that. Okay, so when starting, so to look at traffic models, if you look at models that look at aggregated quantities, so for example, main traffic density and main traffic flow, the model to go is a model that was introduced now 70 years ago, so in the 50s by Lattil, Witten, and Richard, in which they assume that the mean traffic density evolves in time following a nonlinear transport equation, which is this one. And if there are people familiar with fluid dynamics, this is nothing else than the conservation of mass. And what in terms of traffic that means? It means that it just conserves the number of vehicles that you have in your, in your link or in your road. Okay. This evolution of the mean traffic density rho, so is done computed using a flux function, and this is the main assumption that is made on this type of model, is that your flux function is the product between the mean traffic density and the mean traffic speed v, and your speed v will depend only on the density. Okay, and how you compute this flux function? This comes from experimental data. So you plot in a graph density flow your experimental data, then you interpolate, and you obtain, as you can imagine, several ways of interpolation and several ways of finding this function. And we'll see later on how to do this with real data. So the most important thing to remember of this is that what is called the fundamental diagram, so that is this graph flux density, which is a bit the holy grail, if you want, of transportation engineering, because it links the density and the flow. And usually it has one maximum, which is the road capacity, which is phi max. And that phi max corresponds to a critical density, which separates basically free flow for all density less than this critical density, and congested flow for all density greater than this critical density. And then the other parameter that you have is going to be the jam density. So if everyone is bumper to bumper on your road, that's going to be your maximal density. And you can have a Vmax, which is the maximal, the limit, if you want, the speed limit in each road. Okay, so this is what you do when you have one road, 1D. Okay, but now we are interested in looking at what happens when we have on a overall city, what happens. And again, we're interested in the macroscopic approach. So we don't want to see what happened anymore in each link like here, but we would like to see what happens in the overall network. So the first idea which we started with was just straightforward. Why not just use a 2D version of the same equation? Okay, and this is what you see here. So here now the partial derivative in space becomes a divergence term. Your density is a 2D density, like the one you can see here. And the important thing is that you have a flow. And now this flow, since it's 2D, it will be computed by a magnitude part and a direction part. The magnitude part will stay the same, and we'll see in a moment how to calculate the direction part. Okay. Plus, on top, we added a index L. So in general, you are going to have a flow direction. This flow direction can be a preferred direction. If you want to have several directions, you're going to have to add layers on top. So different density will go at different preferred directions. Okay. And they can interact using different interaction expression, and we'll see in a moment how. So again, so how to compute the flow direction? So the flow magnitude is computed exactly like before, but you plot your data, you do the interpolation, you compute the parameters, and you obtain the fundamental diagram. And this will give you basically the magnitude. How about the direction? So there are several ways to go. What we chose to do is have a flux direction will depend solely on the network. So that means that you take your network and topology, and then based on that, you can compute your flow direction by using spatial interpolation. Okay, and the spatial interpolation basically works very simple. So you have a point in your 2D grid, which will be X and Y. And then your flow field, it's you average basically the value of the flow in the road that nearby. Okay, based on how far this road is, you're going to have different weighting parameters, which will tell you basically how the flow will be directed in that area. And as I said before, this will be monodirectional for each layer of density. So if you have a two-way road, one direction will be considered in one density, the other direction will be considered another density. And just to understand how this interpolation works here, if you see a simple Manhattan grid, right? And if you have a small beta, you're going to have basically a smooth flux. So every road comes almost the same. And if you have a large beta, instead, you're going to follow more closely, let's say, the pattern that you have on your network. And you can compute in the magnitudes still in 2D, so the maximal density and the maximal speed. Okay, so here again, the maximal speed seems low, and this low is because, again, city center in Grenoble is quite polluted, so there are policies in order to reduce the speed limits, and so most of the roads in the city center have 30 kilometers an hour policy. So that's why you see quite low speed, maximal speed limit. Okay, so we started working with this model, and we started we wanted to see, first of all, how bad off we were compared to real life. So we took some sensors in the area. So in our downtown Grenoble, so here you have 4. We have data for more sensors, but we wanted to, first of all, reproduce just the fact that we wanted to have just boundary data. And we collected the flux on each sensors for each day, for several days. And then we collected flux and speed. And then we reconstructed the density and the traffic condition using AIMSUN, which is our micro simulator. And then we compared that to our model. So here you see, we've done this with 2 layers only for simplicity. So you're going to see the first direction, I think it's northeast, and the other direction is southwest, or vice versa. I always confuse them. And then you have the overall direction that will basically is the overall density, aggregated density. So you can see it does not bad. It still catches the pockets, can be better. So we started this as a starting point to move on then to other types of models. But before moving on to other types of model, we were started to get a bit worried about this because, as I said at the beginning, PDEs and control theory, especially nonlinear PDEs and control theory, they are they don't go along too well in terms of theoretical results, because the nonlinear PDEs, you have discontinuous solution in general, even if you start with very smooth initial data. And that will mean that the control theory that you can apply, it's fairly limited, and it's limited to specific case only. So far, there's not a general theory out there. So when we looked at this and we said, like, are we sure we want to go this way? What type of control theory then we can apply to this type of problem? And so we looked first at trying to use some to apply some design some control strategy for this type of models. And the main idea was design any control action which can be applied to traffic. So that can be variable speed limit, boundary control, or even simply just track a steady state equation, and then find out if we can do this in 2D. Okay. And this, I must say, was a brilliant idea of one of my students that just graduated, because she found out that you can found the transformation in which using only the network topology and using the flow that you find from your network topology, you can rewrite your 2D equation into a 1D set of parameterized only equation. And that will simplify a lot our problem. So how does this work? So the idea is, so you take, as before, so you have those flow lines that are created by a network. Along those flow lines, those are integral curves of the flow field. So if you are able to transform them into straight parallel line, along those lines, your flow is constant. So you are taking away basically the dependence on one spatial coordinates, which in our case will be eta. And so you can rewrite the system instead of a 2D partial differential equation, just as a 1D partial differential equation. And each equation will be labeled by eta, which will be now the level at which you'll have a constant flow. So the overall control strategy just turns out to be finding this curvilinear coordinate transformation. Because once you have this, then you can apply basically theories from Hamilton-Jacobi's equation, where you can do the dual of the nonlinear transport equation, basically, and use that to solve basically your problems. So with this, we were able to solve a plethora of control problems. Here I just show you 3 examples. So one is, for example, finding the steady state. So you assume you have demand and supply that are constant, and you want to find the time invariant density distribution. So that means that you just have the divergence term that goes to 0. And the good thing about this transformation is that enabled us to find even the analytical solution. So we could actually write down the equation and find the analytical solution of this. And here we took example again from the city of Grenoble, and you can see that if you take an example of a steady state solution done with Jameson, you can find almost the exact same solution by using either a numerical method that discretize your PDE or the analytical solution itself. So if you write down the equation and then you plot that equation, that's what you obtain. And you can do this also in an optimal way, which means find an optimal steady state solution, which is the desired state here. And you do this starting, for example, from a very far initial state, which is your fully congested network. And then you can see that if you track the error, so the distance between your distribution and the desired distribution that you want to find, you're going to go to 0 as time grows. Okay, so this was one example, but we were, as I said, we were interested in boundary control. So can we actually do boundary control on this? And so the idea is the same. So you want to track the desired trajectory starting off your boundary. So you want to design 2 boundary control laws, so your inflow and outflow, so that you can determine or track a desired density trajectory into your network. And again, this is done on the city center network. It's not. And so it turns out that we were able to find how to do so with just by using Hamilton-Jacobi PDE tools and with an additional space-dependent Hamiltonian, so not straightforward again, but with just that trick, it worked by starting from the set of 1D parameterized equation. Okay, and if you look at here in the Grenoble downtown, so here is the desired density that you want. Again, this is just to show you how this works. So that's why it's half in free flow and half congested. So free flow, it's green, congestion is red. It's just so that you can see how it evolves, because otherwise a good control will be to go completely in free flow.
Larry, should I ask questions or just since I'm not on the web?
I think, yeah.
So when you say control, this is like metering the traffic going in.
Yes, yes, yes.
And out, how do you control the out?
So the same with the traffic lights. So we were able to achieve the desired, basically the desired traffic distribution by in a decent amount of time, so 1 hour and 20 minutes, let's say 80 minutes. And again, then you can go nuts in terms of choosing which type of control you want to use. So here, since it was working with boundary control, we tried also speed limit control. So you want to find the different speed limit and find a different maximal speed for your fundamental diagram so that you can actually improve the distribution. And it turns out, so here there are two different ways in which you can do variable speed limits. So either change just the capacity of the road or moving both capacity and the critical density. So I find this nice transformation here. So we went with the second option. And also in this case, by applying Hamilton-Jacobi just theory, you can basically, you start from a certain distribution. This is your desired density, and then by applying variable speed limit, you can actually get to the desired distribution. But this, as the caveat, that still is a bit slower than what we would like to do. So we're trying to see if there are ways to improve this. It's 2 hours a bit long as variable speed limit, but we'll try to see how it goes. Okay, so this seemed promising as first step for what we wanted to do, but it has a lot of pros in terms of control theory. It enables us to find congestion pockets dynamics without actually knowing all the data and all the information inside the network. But there are some cons, and those cons are kind of important for us. So one is that within each single direction, you cannot have crossing flow. And that's a big restriction when you're doing that on a transportation network. And I think that's the main reason why, when we looked before at the model versus the Hamilton simulation, there was not 100% match because those crossing flow were not considered. And also, if you consider just the two-layer model with just, for example, this interaction term that the overall density should be the sum of the two, you might miss out on some mathematical property that then can help you out when you're dealing, for example, with control, like, for example, just hyperbolicity. So anyhow, we wanted to improve this to have multi-directional model and crossing flow without losing the simplicity of the model. So we didn't want to have now a model with, again, going back to a model for each single link, or going back to a model in which we need to have separated traffic areas. Okay, we still wanted to keep the overall idea, and so we went to this model, which is called news model, but has nothing to do with news. News just comes from northeast, west, and south model, and the idea is is as follows. So instead of starting directly from the LWR and then just going to D, now we start from the whole network. We take the equation in each single network, the discretized one, and including the equation in each node. And we do actually the opposite of discretization. So we go from discrete to continue. And that method is called continuation method. And using that method, we try a bit to basically include in the dynamics of the PDE already the dynamics of the junction, which allows us now to consider crossing flows, okay, among the different roads. And the model is a conservation law, so it will be a nonlinear partial differential equation, but it will contain all the properties of hyperbolic PDE systems, including bounded densities. It is scalable, mathematically treatable, can use the same control strategy that we saw before, and we validated then later on what we'll see in a moment using the data from Grenoble. So again, the idea is that now instead of using a road formulation, so here this is what's usually done in traffic. So you have a junction, and then you have one equation for each road here, okay? Now we say we don't want to rely on those equations here, but we want to transform everything in just cardinal direction. So at most we will have 4 equations, one for each cardinal direction, okay? So, but now this means that your flow and density vector are 4D vector at this point, in which you have, for each direction, you're gonna have 1 vector. And to maintain the information about what flows goes into your intersection and what flows goes out, we will separate inflow and outflow, but this will come out just in the mixing term. So when we want to keep the layers to interact one density to another, because at the intersection is the only point where that happens, okay? And you can capture multidirectionality now, because now you can say that your flow, for example, in north will be the sum of the flow that goes north-north, north-south, northeast, and northwest, okay? So this is an example done with the north, but it applies in the same exact way for each one of the directions. So the model, it looks as like this. So no matter how big your cities is, no matter how many links you have, no matter how many nodes you have, your model will be always 4 equations at most. And if you look, you can see basically you're going to have a part, which is the time derivative of your density. Then you're going to have a second part here, which is the transportation term, which is exact same divergence as before, the dimensions of your flow. The only term you're adding is this cosinus and sinus, just to take into account the direction. So before, you're not following the road anymore, you're bringing it back to the cardinal direction. And then now what you're adding on that LWR basically based model is this mixing term, okay, where you have the interaction between the different densities. So that it's what is extrapolated from the intersection, and will tell you basically which percentage of people from each direction will mix with the other ones. Okay, so we validated this using the data from Grenoble again. So this is downtown. This is the extrapolation of graph of the downtown. Here it's all the data that we collected. So here, those are sensors for which we had flow and speed. And then in red here, those are Bluetooth sensors for which we did a campaign just 1 week, just to try and get, at least for the biggest intersection, some kind of idea of how the flow is actually split in the real city. Okay, and so let's see if this works. So here, so you see here, this is the model, and this is the real data one. And now you can see that we are actually capturing very well the different dynamics of traffic, okay? And we can capture the congestion pocket, and we can capture it with relatively no delay also, which is also what is important for us. And so this was a simulation done in a full day. So, and as you can see, wait, I'll do this like this, I can replay it for you. And as you can see, so there's congestion pockets, not too congested because this was done during one of the main confinement we had in France during COVID. So there's a bit of congestion pockets, but especially like in the biggest intersection, but we were able to capture that and capture that dynamically, which is what was important for us. Now here, as you see, when the simulation runs, there's what is called similarity, and here is a percentage. And how do we compute that similarity with respect to the original, the real data? So we use the what is called the structural similarity measure, basically, and the idea is that this is used in general to compare to. Wait, I don't know if people can see this or not in the Zoom, but okay, good. So, and the idea is to compare two images, and this is what is used in general to compare two images. Because comparing to density has a lot of issue in which metrics you must use. Like some people use fastest time distance, some other people use just simply L1, but each one of them has some downsides. For example, L1, if you have delay, you will not able to catch that. And so we decided to go with this one that basically at each time step compare how the two images from the real data and the model density distribution do. It's based on basically the mean values of the distribution, the standard deviation of the distribution, and the correlation coefficient of the distribution. And if you see this, there, so if we look at the overall, basically at the overall over the day parameter, so this parameter goes between -1 and 1, which means -1 you are totally off, basically there's no similarity. 1 means you are similar. So we are in the overall, we are in 75%, which is not bad, I would say. And then we wanted to see like in which area we were actually off, like if that was possible. So we separated the downtown in 9 zones and tried to see which one had the worst in terms of. And so what surprised us was that the areas where we are actually congested, we actually captured them quite well. We are all up here. The area where we seem to do worse is the area 2 up here. That was one that had the least flow. So we assume it's because we had less information with respect to the other areas. Okay, so now what we saw so far, completely deterministic. So you start from your data, and then you supplement your network with the data you have, and then you let your model just run. Okay, and that will forecast your traffic, and if you do control on it, it will forecast how the control does. However, how do we do when something happens that modifies our network parameters or modifies the main assumption that we did on our model, which is the fundamental diagram? Okay, so what happened when we have, for example, there's an accident and now that road is closed, or there's an accident, some lanes are closed, so it means your capacity is reduced. So can we actually find methods to capture this in the model? And how to do this? So the main idea here is trying to, first of all, estimate the road capacity from real data and do that not offline, but do that online if possible. And then we need to see how often we need to do that online. And then we need to see like how much do we need to do that, or if we need to do it like constantly, or maybe we can get off on doing it like only for some times of the day or when something happens specifically. Okay, so just to give you an idea, so this is how our data look like. So this is just for one sensors. This is so you have flow, speed, and occupancy, which is a surrogate basically of density. because it just tells you how much the sensor is occupied over a certain amount of time. So it gives you a percentage of how much person is occupied. So as you can see, basically we have overall the same traffic during the week and then low traffic over the weekend, which seems quite reasonable. Okay, so now given the data we have, can we actually find the best parameters, and those parameters should be found offline, or do we need to find them online? So that's the first question that we would like to ask. Okay, so here I just plotted some data. So here you have density and flow again, and I just plotted on top of this data two types of lines that you can use to interpolate them. I could use any other, like it's not even like. And we want to calibrate three parameters, which is the maximal flow, so the point up here, the critical density, which is the density corresponding to the maximal flow, and the gem density, so the maximal density. And this gives us this parameter set. Okay. We tried several techniques just to find out like what was the best one to see if we could how to calibrate those parameters. And at the end, we realized when we were looking at the Parsons coefficient here you have the capacity, so the critical flow, it's also the capacity, and the critical occupancy, which is the density. It's just, in reality, it seemed to be that flow and critical density have a linear relationship. At least that's what we inferred from this. And then if you look at the flow seems to change basically. It seems to change like during the days a lot, one day from another, and it has a very long right tail in distribution. Instead, if we look at the critical density, it's a bit tighter distribution, so it seems not to have the same issue. And so when we looked at this, we decided, okay, so it's enough for us to say that we have stochastic nature from her parameters, so maybe we should look at the sequential line parameter learning algorithm just to detect like those parameters for our fundamental diagram. So to do so we used a nonlinear state space formulation. Okay, so and given so if you consider y the observed vectors of density and theta the vector of hidden density, then you're going to have the observation equation that is given by the measurements that you have. So that will depend on the type of sensors we have and what type of sensor will be working at this time, plus an evolution, an error. And then we have the evolution equation in which we will have the vector of hidden density computed by using basically Godunov scheme, because we have a type of PDE that allows us to use Godunov scheme. You can use other schemes, so that will be dependent on the model we're using, plus again the error. And then we use the particle filtering to do the actual online sequential learning of the parameters. And again, you do this, and then you plot what you obtain. And here I plot an example. So you have the same fundamental diagram, 2 days. One has no accident, one is with accident. If I wouldn't have put the title up there, I doubt any of you can tell me which day has the accident and which day has not. So, so it works in terms of the fundamental diagram, but then still doesn't solve my problem of trying to find the solution of when we have non-deterministic event or random event that happens in my network. So on the other hand, if I show you the time series of the density of the speed, for example, all of you can tell me which day has the accident, right? Because this is, here you can see the drop in density clearly. Okay. So we realized that we also had to look for learning the capacity, not only in terms of fundamental diagram, but also as a online parameter. And so here you have, so here in blue, it's the median value, for example, for all Mondays of what happened in the capacity of the road, okay, of the speed, sorry, of the road. And then in orange is what happened on the days you have accidents. Okay, and you can see that there's clearly different profile. So we should be able to catch this with our. And so we did this using the particle filtering method that I showed you before. So here you see learn capacity, day without car accident, and here, and the day with the car accident with 5 minutes time. And here you can see that we were able to catch quite well the drop in the capacity due to the accident with 5 minutes maybe delay, but there's nothing we can do because that will depend on the sensors that we have. So it depends on the measurements, how much we can get from the sensors, and we get information every 5 minutes or so. And so that it's the delay that we're going to have in catching the incident. The problem with incident is that it's not only it's a random event, but it's a very sparse event. So you don't have lots of data from which you can learn on an accident. In Grenoble, during a year, you might have something. I don't think we even reach 50 incidents in a year. So you have lots of data that are from days with no accident, and then you're gonna kind of looking for the outliers. But each accident will not influence your data in the same way, okay? Because maybe it's a small accident, maybe one requires you to close completely the road, the other one is just maybe close some parts of it. Okay, so this is mostly what I wanted to tell you today, and where we are now. So what we would like to do is now use this online parameter into the news model, so that we can actually see how it improves the forecast in the days where we have accidents. Since I moved out here, we're trying to move this out now with data from the Bay Area. So we are reworking the whole network and data structure for it. And I have students now trying to see if what we did for accident will work also for hazardous event, where we will have part or complete part of the network cut off because, for example, of I don't know, wildfires or climate change event, and in that case, how the model is going to react and how can we apply control to it in order to improve, for example, evacuation strategies or emergency services. And once we apply this online algorithm into our model, how is that going to affect our control strategies? Is still deterministic control the best way to go, or we need to move maybe to other types of control, for example, reinforcement learning control for 2D models. Okay, and just to conclude, so most of the, if not all the work you've seen today, was done by my students, especially. So Alexandra Malkova that worked on the Grenoble accident part, Stéphane that works on the 2D model, Stéphane Mollier, and Ludmila the brilliant idea on traffic control, so Ludmila Tumash, they just graduated in September. And then also thank you to my collaborators, Julian Herbel for the statistics part, and Benjamin Seibel for the modeling part, and Carlos David that helped us with the control part, plus all the data framework and all the collection of Grenoble network data. And thank you very much. And if you have any questions.
Well, let's ask Larry, you have online questions?
No, there are no questions yet. Go ahead if you have a question.
Let me ask some questions here just to get started. So, you know, a lot of interest, of course, in this real-time tolling. So what is your sense of how you can influence traffic patterns through putting, I mean, so this has been, that's what I was asking you about boundary control. Boundary control is at the edges.
Yes.
So, on the other hand, taxes are like a full contact sport, you know, during the.
Yes.
So how would, and also, so that's one question, second question that you can do as much as you can till other questions come.
the technology for those, for doing the PDEs and those control, what was the technology that went into improving those control laws?
Okay, so for the, okay, I'll answer the second one first, that's easier. So for the PD, so there we used mostly it was, so once we used the transformation to get to everything in 1D, so mostly what was used is transformation to Hamilton-Jacobi equation, and then used the Hamilton-Jacobi equation to solve the control problem. And that can be done for traffic problems with specific fundamental diagrams, so it's not a general result, can be done analytically, the computation of the control. But you need to be specific on your fundamental diagram. I think what we proved analytically was proved for the bilinear fundamental diagram, so not fully nonlinear. And we have though managed to get results, I think, for mixed regimes, so when you can jump from one side to another.
And then, so the other question.
So the other question, again, can you repeat me? What was
The question was, you know, there's a little bit of a mad rush in cities to do this real-time coding.
Yes.
And of course,
yes,
the issue is real-time coding really. So this game here is all interested in the real-time coding. So maybe you guys should ask it. So anyhow, how would you? I mean, would it'd be interesting. So how would you? Could you adapt some of these techniques to really do that kind of distributed control?
Yeah, that's a good question. Probably, so to do it, if you want to have control on each intersection, which is what the real-time coding.
Let's just call it a few arteries.
So if you have few arteries, and you could potentially apply it, but what I'm thinking of is that probably. Okay, so it will depend.
London and City of Singapore do, and what New York and Washington.
Yes, yes.
So they have, you know, they've identified some four. You probably know this better than me.
Okay, so what you probably will want to do is, so to use that framework, I think you'll have to recast it in something, instead of boundary control, it will probably become something more similar to what is done for the variable speed limit, which means that you're going to have some rate or control rate that multiplies your flux function. That will depend on your space position. So it will not be everywhere in your all areas. And then the math, I don't know if it works, we'll have to work it out, but that's how I will go with it, probably. That's a way to go, I think. It would probably be implemented on the flux function more than as a boundary control.
Go ahead.
Yeah, thank you for the talk, Professor. I had a question about the two-dimensional models where you linearize the integral curves of that entropy. So my question is, how does that work when, you know, in certain cities, traffic not only flows sort of in a direction out, but in some cities it circulates, like Washington, D.C., you get traffic, you know, goes from one point and then circulates around the curve and then sort of comes back on the other side. So how do you go about linearizing?
Okay, so that's exactly, so the second model won't have that problem because you can have circular, it's even included in the model because you have the same in the inflow and outflow, you have the terms that are included in north-north direction. So in there won't be a problem. In the first model, and that's why we moved to the second model, that's definitely a problem because you cannot have circular flow, basically. You cannot have, because then you're going to have lines that intersect. You cannot have flow lines that intersect. Yes. But if you do the second model in which everything is brought back basically to cardinal direction, there you'll never have that problem of having the circles. So you can actually do that in that model.
So thanks for the talk. I have a question about like how do you reconcile this setting where you are describing the controlling the like integral curve so that congestion is reduced. This is kind of a central authority perspective of making something good. but each individual particle in the flow is selfish agent in itself. And
This is their big interest area. So,
That's a good question.
so the thing about the tolling and all of that is that in some ways it is to encourage this Nash equilibrium.
Yes,
And so these guys are interested in really how do you incentivize behavior.
I see.
And of course, but not having the tools to identify what happens, I think all these decentralized strategies, nobody's able to assess them.
Yeah,
So.
yeah. So, okay, that's a good question. So when we start looking at this, we have not even thought about the centralized, because again, the city of Grenoble is very centralized approach in terms of control of the stuff. So they wanted something that's at the overall level. If you want to, I guess again in the second model, that I will insert it probably when you're constructing the model going from the news model. When you are constructing from the intersection, there you have we are including we're included the part where you have split ratios or origin destination matrices, and the origin destination matrices you might include what people tend to do, but it's still not behavioral related thing. So I don't know if you can insert behavior here. That will probably do with something like routing. But
So this is why we wanted to call you here, because we'd like to pull you into these discussions after your talk. So
that's interesting.
When you talk about this digital transformation, it is really this sort of mechanism design. How do you incentivize? I don't know if there are people on the call.
I don't know.
Any questions on the call, Larry?
No, nothing yet.
So Lillian is, I don't know if she's on the call. If she is, maybe she can hear me. The University of Washington. So she has been working with, this notion of how do you incentivize, how do you reduce congestion in downtown areas? Because a lot of congestion is actually people circling around looking for parking.
Yes.
And so the cities have these parking apps, which are to tell them, where to look, where to give up. And the tension is between people who want to control congestion with the city authorities and the shopkeepers, who actually don't want the city to maximize its parking revenue because, there's havoc with their business. So those are the kinds of questions that
Yes.
So Lillian, she's not on the call.
So Grenoble is a different approach in the sense that the city is trying everything it can possibly to kick out the cars from the city center. Yes. So they are incentivizing a lot of transit. So to go into the city, you're going to have to park outside, take transit, and get to the city center. That's the approach they are taking. I would say, parking structure and how that can be influenced, that can be included in the model by adding source and sinks in some location, and that will take it into account the people that leave the parking and actually go into the parking. But to model behavior, so if you want to model the behavior, then you're going to have a different type of, I think, model. So
So modeling the utility functions is yet another story.
Yes.
Let's say that this has been identified for you the way you identified your fundamental curve. But even with that, there's questions about whether people are willing to trade off time and money, which and even this picture that you have here, this idea that a few well-behaved people can make the overall traffic. So we wonder if there is an explanation for that out of this sort of utility models that people will have.
I see. Okay, so about this, so I've been reading a lot on how people behave when they interact with things that they know are, for example, automated vehicles or connected and automated vehicles. And I don't think we have yet all the information that we need in order to derive that in terms of modeling, because we don't have specific drivers' behavior. We have we have the data from the connected automated vehicle side, but it's hard to get specific data trajectory for human sides, especially in this interactive environment.
Very interesting. Well, your tools are quite interesting and fantastic. All right. Go ahead. Sorry to hog all the questions. But,
That's okay.
people on the Zoom seem quiet. So go.
Yeah, so another question about how you, so I think in the first few slides of your talk, you had, this way of taking a vector field that's defined on, in 2D and sort of almost projecting it onto the network topology. Could you talk a little bit, and you had some parameter that governs sort of how closely the vector field sort of
Yes, so
matches
this
the-
one I
the
think, let's see.
Yeah, could you just sort of give some more
So there are two parts. I kind of skip on one part because in interest of time. So here it's just really spatial interpolation. So you pick your roads, you pick the values on the road, so you compute the specific fundamental diagrams parameters in the road. That could be your capacity, your speed limit, and your critical density. And then you do spatial interpolation for the direction only with it. Okay, that's how you can just do the direction modes basically. So you're picking the direction from here, direction from here, direction from here, and then you kind of unify them in a unique information. What is not seen and what is instead done in this case. So here instead it's using a kernel density estimation. So here what you do, for example, for the maximal density, you take your whole network, you pretend that you put cars bumper to bumper in the overall network. And then with that, you kind of create a kernel Gaussian distribution on top of each single car, and then you smooth out that to become in 2D. Okay, and that's what's done for the maximal density, and if I'm not wrong, also for the maximum speed, maybe.
Okay, just to keep people on the, Larry, if there are no further questions, I'd like to thank our speaker, and we'll continue with her offline here. Larry, are there things that we should address or?
No, this is great talk. Thank you.
Thank you very much. Music, only a few people clap.